Summit 2015. On behalf of the organizers, the MIT Water Club, I would like to extend my warm welcome to all the speakers, panelists, and our guests today. In its third year of running, the MIT Water Summit gathers industrial experts, researchers, and professionals from diverse backgrounds to come together to discuss the most important challenges and opportunities in the water sector. And this year, we are focused specifically on the challenges facing the water sector due to climate change. For every company, government agency, researcher, and the audience member here today, the water may mean a different thing. For some, it's flood protection, drought response, urban resiliency, entrepreneurship opportunities, or industrial processes. However, all of us can agree that we are working towards improving the importance of water for sustaining life and supporting our way of life. During the next 2 days, we will have panel discussions to explore questions like, what are the climate-driven water challenges? How is cutting-edge research changing our ability to understand and anticipate these challenges? How is technology and innovation equipping us to build more resilient water systems? And how can all these groups, businesses, civil societies, governments, and researchers work independently and together to build a more resilient world? On a lighter note, although for our panelists today, we have a bottled water, but the official drink for the event is Boston tap water. We don't want to start a bottle versus tap debate because one of the Water Club sponsors is the PepsiCo. So all we can say is, if you get thirsty, drink Pepsi, or better yet, enjoy the wine and beer at the open bar during the reception today evening. In addition to PepsiCo, the Water Club and the Summit have a variety of sponsors, without whom this event would have not happened. Those indispensable sponsors include our primary supporter, the Abdul Latif Jameel World Water and Food Security Lab. We are also extremely grateful to Gradient, Arcadis, DSALTech, and the World Resources Institute, MIT Departments of Civil and Environmental Engineering and Urban Planning, MISTI Brazil, Israel, and the Woods Hole Oceanographic Institute. Thanks for supporting the MIT Water Club and making this event possible. Okay, so now without much further ado, I would like to now invite Professor Leonhart. Professor Leonhart is a faculty member in the Mechanical Engineering Department at MIT. His research focuses on water purification and desalination, heat and fluid flow. He also serves as a director of the Abdul Latif Jameel World Water and Food Security Lab at MIT, and also as a faculty advisor to the MIT Water Club. So please welcome Professor Leonhart.
To do the equipment swap first. But fortunately, it gets easier and easier, I think, as the equipment gets more and more standardized. Everybody's using Macs now. So let's see if it works. That's promising. Yes, okay, so you're looking at Kyoto, but that's not the point of my talk, that's just my background slide. I wanted to say a little bit about what we're doing at the Abdul Latif Jameel World Water and Food Security Lab and some of the things happening here at MIT in connection particularly with water, but also food. The name of our lab is long, and so we have an acronym, JWAFS, which is short and easy to say, so JWAFS. I'm the director, Renee Robbins is the executive director. We've been looking at problems at MIT such as the one that's illustrated here. This was the RLC. It was the fourth largest freshwater lake on the planet with a volume equivalent to Lake Superior plus Lake Ontario, about 68,000 square kilometers of surface, with cities and economies based on it. The rivers feeding it were diverted in order to grow cotton in Uzbekistan, with the result that this lake has dried up completely and wiped out the cities, wiped out the fishing economies, and everything else that depended on it for its existence. And this is just one example. In California, if you go to the Colorado River, very little water crosses the border into Mexico at the edge of California. Almost nothing flows to the sea. Owens Lake is gone. And around the world, there are rivers and lakes that have been completely depleted because we need water for our cities and for our agriculture. But more subtly and perhaps more insidiously, we're also overpumping groundwater around the world. And water tables have dropped dramatically. Portions of the Central Valley in California have fallen by tens of feet over the years. And the exact extent to which we've depleted underground water is, frankly, not really very well known. But we know it's a huge problem. What's driving all of this, as much as anything, is the continuing rise in our population. Over the course of my lifetime alone, I expect that population will triple. Since 1927, well, in 1927, the world population was 2 billion people. It's more than 7 billion today. By 2050, it'll be 9.6 billion. Almost 5 times as many people over a period of just 130 years or so. And this growth, more than anything, drives our demand for water supply, and it's driving the overconsumption of our water resources everywhere. But in addition, it's coupled to our production of food. About 70 to 80% of the world's water withdrawal is for the purpose of irrigating crops. About 40% of the Earth's ice-free land is currently used to produce food. And the demand for food continues to rise. UN estimates suggest that we might need 70% more food by 2050 to feed all those extra people that I mentioned. It's clearly not possible for us to increase the amount of cropland we have by 70% by 2050. We're already using most of what's easily available, and it's not obvious that we would want to cut down more tropical rainforests in order to support that kind of thing. So there's a challenge. We've met the food challenge in part through technology, through mechanization of agriculture, through artificial fertilizers, and of course through irrigation. But this comes with consequences and costs as well. It's estimated that 1% of the world's energy goes to produce ammonia-based fertilizers, to fertilize these crops. Agriculture is a major source of greenhouse gas emissions around the world. And there's good evidence that the conversion of rainforests to farmland affects evapotranspiration, which then alters rainfall and other sources of water for us. So there are challenges in the way we're approaching this problem. Some of the consequences are, for example, writ large on Lake Erie here. Runoff from the cities and farmlands surrounding this lake have produced major algal blooms in the lake many times. Last year, they had to shut down the water intakes in Toledo, Ohio, because of toxins from these algal blooms. And so again, you ask the question, are we growing our food the right way? And look at the impact that it has on our water supplies. Further, we waste a lot of food. For all of our agriculture, there are still about 800 million people in the world who are underfed. Yet we waste enough food to feed those 800 million people 4 times over. And so there's a question about how we use food and where it's located, where it's distributed, and how the costs are managed. So from all of this, MIT looked at these problems, we thought deeply for a number of years, and we concluded that population growth, development, rising standards of living, urbanization, and climate change pose major challenges to our supplies of water and food. We're not pessimists, however. We believe that science, technology, and business innovation, urban planning, can all contribute to the solution of these issues, and that by putting our heads together and working hard on these challenges, we'll find answers, and we'll keep things going without destroying the world that we live in. And this summit, over today and tomorrow, is devoted in part to looking at ways that we can address these challenges, particularly in the area of water, and particularly around the challenges that are raised by a changing climate. MIT has responded to these issues by the creation of an institute-wide laboratory or initiative around water and food. This is JWAFS, as previously mentioned. Our mission is to work with all departments and schools of MIT to bring in resources and to push them back out to the faculty and students so that they can undertake these challenges. And we are progressing with our mission. I will tell you a few of the things that we've been doing. In 2015, we've awarded more than $2 million worth of grants on campus. These grants support research and they support technology transfer. In the area of research, we gave seed grants this spring to 9 teams spanning 11 departments in all 5 schools. The groups are working on topics like food science and food safety, topics like water supply and water technology, topics around environmental science and environmental engineering, and topics around development. And that work is progressing. I'll show you a couple of examples. In addition, we have a program collaborative with the Deshpande Center for Technology, Innovation, and Transfer, where people who have an idea for a new business that needs a little more support. They need critical experiments, they need to write a business plan, they need to find venture investment. We will support those people for a year or so that they can get the necessary steps taken and spin the technology out into the world. And this is motivated by a belief that business innovation can affect the world we live in. This is an example of one of the projects that we're sponsoring in the tech transfer area. This is a project by Professor Sinsky in biology, Professor Strano in chemical engineering, where they're looking at the use of optical resonance in carbon nanotubes to detect contaminants in water and or food. They have technology that will allow them to coat the nanotubes so that when a particular analyte binds to it, the fluorescence of the tube shifts in an identifiable way. They can detect gluten in food, they can detect heavy metals, they can detect biota as well in water. And so their concept is to have a multiplexed array of these tubes that can sample simultaneously for, say, all the heavy metals and all the potential bacteria in a water sample. Perhaps a handheld device that can be carried and used on site. We have a project that's related to water sampling in the developing world. This is with Professor John Hart, Professor Rohit Karnik, and Chetan Vaishnav in the Sloan School. They're interested in how you do water sampling in the developing world. You have a challenge when you sample water that it's typically done by taking a liter or so of water in a jar, fixing it in some way, and then sending it to a laboratory. So you've got a transportation problem, a sample management problem, and a storage problem on the other end. They would like to adapt the same kind of technology that's currently used for blood samples, where you can put a dry spot, a spot of water onto a card, let it dry and let it go, ship the card off to a lab, only the card by mail. The card can be put on file, or it can be tested when needed, or it can be tested immediately. So you develop an archive of water samples that can be used to track outbreaks or infections, or that can simply provide a convenient means for villages to do sampling on site. They're doing this work collaboratively with the Tata program at MIT, and they're working in particular to try and make sure they don't simply have a technology, but they have something that fits within the social fabric of these villages so that it will be adopted and used. We have a project that's being done by Professor Susan Solomon and Dr. Ken Strepek, who will speak later. This is about looking at how climate change is likely to impact food and water security in Central Africa. As it happens, there are parts of the world where today you can do climate modeling with sufficient fidelity that you can pick out trends with uncertainty and actually make predictions of where things are headed that are reliable enough to be actionable. So they're doing these simulations for Central Africa, and they are going to communicate these results back to the governments in those areas so that actions can be taken. They actually have the kind of boots-on-the-ground connection that will allow them to reach policymakers in the area. You may have seen the flooding in Houston recently. Perhaps it's a foretaste of things to come. In fact, I'm going to Houston on Monday, and I'm told that there's going to be a huge storm there again. So I'm going to see it for myself, I hope. I hope not. There's also concern as to what's going to happen in cities like Los Angeles under the current cycle of El Nino. So when you have urban stormwater, you have two problems. One is managing the urban stormwater so that you don't get flooding, but the other problem is, can you retain it and use it? Use it for groundwater recharge, or actually use it to supplement the urban water supply. So we're funding Alan Berger in the Center for Advanced Urbanism and Heidi Nepf in the Parsons Lab for Environmental Science and Engineering to look at this question. How can you design these and how can you weave them into the fabric of cities? We're also funding Professor Jeff Grossman in Materials Science and Engineering to look at the use of reduced graphene oxide as a means of extending the concept of a graphene desalination membrane to something that's more easily fabricated. The big challenge with graphene is, how do you make it at scale? He's got some ideas. So those are some of the things that we're doing on the research side. We're also working with the MIT Water Club around this event, and also in connection with the Water Innovation Prize. Here's a slide for the Innovation Prize. They've already had their generator dinner with a number of teams now formed, a number of attendees, and $20,000 worth of prizes. So it will be very interesting to track this and see what comes from the event. We have separately made an arrangement with Rabobank to launch a Food Innovation Prize. And the generator dinner for that will be held on Thursday the 19th here at MIT. We have a lot of excitement around this idea too. So that's what I wanted to tell you about JWAFs and the kinds of things we're doing. We're optimistic that MIT is going to rise to be a major presence in the area of food and water, that we're going to have very substantial impact on the world's challenges in these areas, not because of anything that the JWAFS people themselves are doing, but because JWAFS is engaging the entire community. It's the MIT community that brings these strengths to the problems at hand. That being said, I'll stop here and we'll move on to the next part of the program.
Thank you, Professor Leonhart. We'll now begin our first panel, the interpret, and I would like to welcome the panel moderator and the panelists to the tables. Yeah, please welcome.